of energy storage, and then we looked at electrochemical energy storage in particular, and I said that we will be focusing on heat transfer aspects related to electrochemistry, and so I think it's a good idea at this point to look at some fundamentals of heat transfer itself, right? So in this lecture, we will not talk about batteries as much. I want to lay down some fundamental principles of heat transfer so that in the coming lectures we can integrate the two, batteries on one side and heat transfer on the other side. So in this lecture, we talk about what heat transfer is, how does heat flow, what are the various mechanisms and equations that govern the flow of heat, and so on and so forth, right? So let's start with a very simple example. Suppose I have hot tea. I take this hot tea and I keep it out on a table. What happens to this hot tea as time passes? It gets colder. Clearly, it gets colder. Or instead of a hot tea, if I have a hot metal ball, this metal ball has just come out of the oven, some manufacturing process, right? I lay it down, and as time passes, its energy goes down, right? How do I characterize its energy? What is different between this hot tea and the tea after some time, which has now become cold? How do I tell that this is hot tea and this is cold tea? Temperature, exactly. So the temperature, T, is the quantity that characterizes the content of energy in this body, right? It's like a measuring tape. Whether something is very long or very short depends on how it scales, right? How does it measure using a scale? And similarly, the energy content of this body, any body, is characterized by its temperature. The higher the temperature, the higher is the amount of energy in that body, right? I can measure temperature in many different ways. The simplest way is, how do I simply measure the temperature of this tea? Put my finger in it, right? If I put my finger in it, my finger will immediately know if it is hot or cold. And there are many other ways of measuring temperature, which we will look at perhaps on Thursday. But for now, all I want you to know is that temperature is the characteristic quantity that governs the energy content of the body. The higher the temperature, it means that the greater is the energy content in the body. And if I have a body at a high temperature, suppose I have a hot body, and by now you know that hot means high temperature, right? And suppose there is another body which is cold. And suppose I get them in contact with each other. What will happen?
Heat exchange.
Heat exchange will happen. Heat will flow from hot to the cold side. So that the temperature of the hot body goes down, the temperature of the cold body goes up until the two temperatures become equal to each other. So if I was to plot temperature versus time, the hot body temperature will probably look like this, the cold body temperature will probably look like this, until the two of them are almost the same with each other. This process is called heat transfer, the flow of heat. I'm using the word flow as if it's a liquid. We use the word flow typically with liquids, right? We also use the word flow with heat because heat in many ways behaves like a fluid. It's really not a fluid, clearly. Historically speaking, in fact, 200-300 years ago, people like Fourier, etc., when they first discovered heat and the flow of heat, for some time it was believed that heat is actually, in fact, a fluid that we cannot see with our eyes. A hot body has a lot of that fluid, a cold body doesn't have a lot of that fluid. If you connect the two, the fluid will flow from the hot body to the cold body, just like a bucket. A bucket is becoming our good friend here. If I have two buckets, and if this bucket has a lot of fluid, and if this bucket doesn't have a lot of fluid, and if I connect the two buckets, what will happen? The fluid in the in the bigger bucket that has a lot more fluid will flow into the bucket that doesn't have a lot of fluid until both of them have the same level, right? This is exactly the same way heat flows as well. The hot body that has a lot of heat will transfer its heat to the cold body that doesn't have a lot of heat until the energy content of the two become equal to each other. So you can see that the flow of heat and the flow of fluids are actually very similar to each other. In fact, we will learn that the equations that govern heat flow are actually very similar to the equations that govern the flow of fluids. Yes. Any effect on the? Yes. In this case, there is a there is a transfer of mass, right? But here, there is no effect on the mass. As heat flows from the hot body to the cold body, it does not carry mass with it. The weight of the hot body and the weight of the cold body will remain the same. Sorry? The density, no, the density will not change here. There is no transfer of mass that occurs. Only heat flows. But mass does not flow, at least in this simple example. Do you see what I'm saying? Do you understand what I'm saying? Cool. The flow of heat must govern several fundamental laws of physics. If I just have a hot body and if I just have a cold body, there will not necessarily be transfer of heat from one to the other. First of all, there must be a connection between the two, right? Secondly, there must be a temperature difference between the two in order for the heat to flow by itself, right? If I have a cold body and a hot body, heat does not flow from the cold body to the hot body spontaneously, right? A glass of water sitting here will not by itself become hotter and cool down the room. I wish it could happen, but it does not happen, right? There are fundamental laws of thermodynamics that heat transfer must obey. The first law of thermodynamics is that energy must be conserved, which means that if 100 joules of heat leaves the hot body, then barring any losses, leakage, etc., exactly 100 joules of heat must be gained by the cold body. I cannot create or destroy energy. That's the first principle of thermodynamics, and heat transfer processes must satisfy the first law. Question? Yes, it will, and if yes, the volume might change. Yes, sure. We are neglecting those effects here.
That's what we call as thermal expansion.
That is what is called thermal expansion or contraction, but we are not worrying about that right now. Those are minor effects. Yes, in that sense, you're absolutely right, the density might change. But there is no bulk motion of the mass. It's not like the hot body will lose its mass as well. Okay?
Transfer of heat takes place to the nearest neighboring atom which can contact it.
Yes, absolutely. So the first law says that whatever heat is lost by the hot body must be gained by the cold body, and I cannot by myself create or destroy energy. The second law, which in some ways is much more interesting, talks about the spontaneity of this process. Roughly speaking, it means that if I have a hot body and a cold body and I connect the two to each other, then heat will always flow spontaneously from the hot body to the cold body and not the other way around, right? And that is indeed our usual experience. If I bring a cup of coffee and if I put it down here, the coffee will cool down, the room will heat up at the expense of the coffee, and all of this will happen naturally, spontaneously. That is how nature wants it to happen, right? But now we come in to this picture, and there are so many occasions and systems around us where we want to go against the will of nature. I have this room, I have the outside. On a day like this, the outside is very hot, the room at the start of the day will be cool, right? If I do nothing, what will happen as the day passes? This room will heat up because of the heat outside, right? But we want it to happen the other way around, right? For our own comfort, we want to remove heat from the cold body, the room, and reject it to the hot body, right? Sink to source rather than source to sink, right? And the same thing happens in a refrigerator. I take a bottle of water, I want to cool it down, I stick it inside the refrigerator, and I want the heat to go out of that bottle and to be rejected to the room. In the sense that I am trying to go against the direction of spontaneity which was determined by Mother Nature. So the second law says that if I want to do it the other way, it is not impossible to do, right? I can take a cold body and I can make it cooler. I can remove heat even from the cold body if I want. But in order to do that, I will have to pay a price. That is what the second law says. And what is the price that we pay for that? Electrical work. So I take this room, I can make it cooler. I can take that bottle of water that I put into the refrigerator and I can certainly remove heat out of it. But in order to do that, I have to pay the price of electrical work. I have to connect it to the power grid and I have to do electrical work in order to go against the will of nature. So provided these two laws are satisfied, heat will flow from one body to the other. Yeah? Any questions so far? It turns out that there are three mechanisms of heat transfer. Three modes of heat transfer. The first mode of heat transfer is that if I have a body, a solid body, and if I expose it to hot surroundings on one side and cold surroundings on the other side, then heat transfer will happen from the hot side to the cold side. Right? And this is something that we experience all the time. I take a cup of coffee, I take a spoon and I dip the spoon into the coffee. What happens to the temperature in the spoon? It slowly becomes hotter and hotter, right? How many of you cook? Right? You've experienced this. You're cooking something, you're cooking something, you take the spoon and if you leave it there, you go do something else and then you want to stir it, you come back and you touch it and it's gotten very hot, right? And it almost burns you if you are not careful, right? That is this process in which heat flows from the hot side to the cold side of a solid body. Here is this liquid, here is my spoon. One side is hot, the other side is cold. Heat transfer will happen from the hot side to the cold side. Okay? Now, not all spoons are the same. If I do this with a steel spoon versus a wooden spoon, you will realize that the hotness experienced on the other side is very different, right? A wooden spoon will not conduct a lot of heat. This process is called thermal conduction. And it turns out that the amount of heat that flows depends on the material. If I take a if I take a steel spoon versus a wooden spoon, the amount of heat that will flow across the two will be very different from each other. Mathematically speaking, the amount of heat transfer that occurs is given by a very simple equation: Q double prime equals negative K dt dx. So if this is the x direction, then this equation, which is called Fourier's law, basically predicts that the amount of heat that will flow due to thermal conduction is proportional to the temperature difference, the temperature gradient in that solid body. It does. The cross-sectional area comes into picture because Q double prime is written in terms of heat flux, watt per meter square. Okay, so what is Q double prime x? Q double prime x is the amount of energy that passes in the x direction per second per unit area, joules per second per meter square, which translates to watt per meter square. Yeah. On the right hand side, I have negative K dt dx. dt dx is the temperature gradient across this body. How many Kelvin per meter? If the temperature difference between the two is larger, there will be more flow of heat. Yeah, if I take this spoon and if I stick it into lukewarm soup versus very hot soup, clearly the second case there will be more heat transfer and the spoon will get much hotter compared to a lukewarm soup. So clearly this is consistent with our own personal experience, right? This equation is it passes our common sense test. Finally, the negative sign exists because the flow of heat in the spontaneous manner will always be opposite to the temperature gradient. If the temperature gradient is negative, as it is in this case, then heat will flow from in the positive x direction. Do you see what I'm saying? If it was cold on this side and hot on the other side, then the flow of heat would be negative. The flow of heat will be in the negative x direction. That is the reason why we have a minus sign here. And K is the constant of proportionality, which is often called the thermal conductivity. It is a characteristic of the material of the body. Different materials have different values of the thermal conductivity. A steel spoon typically has a high thermal conductivity. A wooden spoon typically does not have high thermal conductivity. That is the reason why the wooden spoon does not get very hot. The steel spoon does get quite a lot hot. Okay. I want to make a few more comments here. The first comment is that this thermal conductivity is in general a function of direction. Imagine a three-dimensional Cartesian world. The thermal conductivity in the three directions x, y and z could be different from each other. In most materials that does not happen. If I take a block of copper, then the thermal conductivity of this block of copper in the x, y and z directions is expected to be the same, right? However, if I take a composite material such as carbon fiber composites, in which I have fibers of carbon embedded inside a plastic matrix, and these kinds of composites are used very commonly these days, right? What is the most common example where we use composite materials? Sorry? Buildings, yes, absolutely. Sorry? Automobiles, aircraft. Traditionally, aircraft was typically made up of aluminum, but now most aircrafts are made up of carbon fibers. Exactly, carbon composites. So in carbon composites, what we have is that you have carbon fibers embedded inside a matrix of some other plastic or polymer, and in this case, you can clearly expect that heat transfer in the three directions will be different from each other. Along the direction of the carbon fiber, heat will be able to flow very easily, whereas in the other two directions it may not be able to flow that easily. And so in this case, heat transfer will be anisotropic or orthotropic, whereas this, the heat transfer is mostly isotropic. The word isotropic means independent of direction. It will happen the same in all three directions. It turns out that heat transfer in lithium ion batteries is highly anisotropic, and we will talk about that in the coming lectures, the reasons behind it and what it means and so on and so forth. By the way, what are the units of thermal conductivity? You can see exactly from this simple equation you can say that this must be watt per meter Kelvin. What are typical numbers for thermal conductivity? For copper, absolutely around 400 watt per meter Kelvin. For wood, I don't want to take the example of wood.
So we used to study for the release method, it's coming around 0.02.
Yes, absolutely. For plastics, for wood, mica sheet, those kinds of materials, the thermal conductivity is much lower. It's of the order of 0.1 to 1 watt per meter Kelvin, very low. Sorry, this thing sometimes does not, yeah, 0.1 to 1 watt per meter Kelvin. These are typically good conductors of heat and these are typically poor conductors of heat. And in the coming lectures, we will see where lithium ion cells fall in this regime. Any questions so far? Finally, I also want to say that thermal conductivity itself could be a function of temperature. As the temperature changes, it is possible that the thermal conductivity of the body also changes. Typically, oftentimes, we neglect that temperature dependence. We assume the thermal conductivity to be a constant number, but that may or may not be the case always. Okay? What else do I want to say here? I think that is all. So the second mechanism of heat transfer is called convective heat transfer. And convective heat transfer is the heat transfer that occurs due to relative motion between a fluid and a solid. So you need to have a fluid and a solid. When I say a fluid, the word fluid could refer to either a gas or a liquid. So if I have a solid body such as a plate, and if I blow air over this plate, then if the plate is hot and the air is cold, then as the air passes over the plate, it steals a little bit of heat from it. It scoops a little bit of heat and takes it away with it, because of which this air will get hotter and this plate will get colder. Okay? It can certainly happen the other way also. If this plate was cold and if this air was hot, then due to convective heat transfer, some of the heat will flow from the air into the plate. Yeah? Can somebody give me one example of each case where I have a hot solid body and some cold air blows over it? Where does that happen?
Extraction process.
Sure. Cooling of a transformer, absolutely, or any electronic device. There are so many electronic devices, a computer chip, a semiconductor device, etc., MOSFETs and all that, that get very hot. I blow air over it, because of which the solid body cools down. Right? Any examples of the opposite where I have hot air blowing over something cold, causing it to heat up? Welding? No, not quite. External unit of an air conditioner, yes, absolutely. In the external unit of the air conditioner, I have, or the internal unit is it? Internal unit, where I have basically a, a series of tubes that carry some cold fluid, right, over which I blow hot air or room temperature air. Because of this process, the air gets cold, and that is the air that comes out of the ducts and cools down our air conditioned room. Right? This process in which this hot air is able to transfer some of its heat to the pipe and become cold is also convective heat transfer. Finally, I want to bring your attention to the word relative motion, which means that either the air or the solid plate could be moving. In this case, I have the solid plate is stationary and the air is moving. But there are also engineering examples where the opposite happens. Can somebody think of an example?
The lathe operation.
Yes.
They used to have the lubricants over there.
Yes.
Both will be having a relative.
Yes, absolutely, absolutely.
Cooling of IC in the pipe. In stationary air.
Yes, absolutely, absolutely. The air there is stationary and the car is the one that is moving. An aircraft is another example. When an aircraft flies, the air is sort of stationary and it is the aircraft that is moving through the stationary air. And even in that case, there is heat transfer that occurs between the two. Right? There needs to be motion and there needs to be a fluid and a solid body. That is when convective heat transfer occurs. Just like in the previous slide, I had given an equation, a very simple equation for conduction heat transfer. Similarly, the equation for convective heat transfer is also very simple. On the face of it, it is Q double prime equals H delta T. Actually, an extremely simple equation. What it says is that the amount of heat transfer that will occur between the plate and the air, this is Q double prime, per unit area, is given by the temperature difference between the two multiplied by this coefficient called H. This very simple equation is called Newton's law. So Isaac Newton, in addition to discovering gravity, also discovered this very fundamental law of convective heat transfer. So you can say safely that convective heat transfer is studied only by the most brilliant students. Okay? We are all following in the footsteps of Isaac Newton here. H is called the convective heat transfer coefficient. As you can guess, H has units of watt per meter square Kelvin. Okay? What is the meaning of H? H basically captures the fluid mechanics of the relative motion. In other words, H governs how well the flow and the plate are interacting with each other. Imagine if I have two cases, I have the same plate in both cases. In one case, I have air coming in at 1 meters per second. In the other case, I have air coming in at 100 meters per second, let's say. In which case do you expect more heat transfer to occur? The first or the second case? Okay, let me give you another example. You have a cup of tea and you want to cool it down because you want to drink it. What do you do to cool it down? You blow on it, right? The harder you blow on it versus the faster it will cool down, right? The relative motion, the extent of motion, the velocity of motion plays a very big role in determining the amount of heat transfer that occurs. And that is captured by H. The heat transfer coefficient H is a function of the velocity, the properties of the fluid, and the geometry. Velocity you already saw, right? The nature of this fluid also makes a difference. Whether you blow air over this solid or you blow water over this solid also makes a difference in how fast this solid is going to cool down. Because of its properties, water will be able to remove a lot more heat compared to just plain air. And finally, the geometry of this plate also makes a big difference. Imagine if I have two plates. I have one plate that looks like this. It's a smooth plate. Versus, I have a plate whose surface is rough. If they're at the same temperature, if I blow the same amount of air across both of them, in which case do you expect more heat transfer to occur? Not smooth. The rough one, yes. Why? Yes, because it is able to come into touch with it more intimately, this air that blows over it. Right? Whereas the smooth plate, the air just glides, just passes over it, does not have an opportunity to really get to know the plate. Right? So if the plate is rough, in other words, the geometry of the plate also makes a difference in the extent of convective heat transfer that occurs between the two. So there are a bunch of convective heat transfer correlations. That are equations which create a connection between H as a function of the velocity, the properties, nu, alpha, etc., and the geometry as well. So, yes. Sorry? Good question. If the change in pressure causes a change in velocity, then yes. But if the velocity remains the same and you change the pressure, then that by itself will not change anything. Okay? The pressure can also change the properties of the fluid. So it can have multiple effects on each of these things that ultimately affects the heat transfer coefficient.
But Boyle's law cannot calculate it.
Boyle's law can predict that. Boyle's law, PV equals nRT, exactly, yes. So, yes. That's a good question. The properties of the plate do not affect the convective heat transfer between the two. The game of convective heat transfer is played entirely on the basis of the properties on the air side. Whether this plate is made up of wood or it is made up of copper, as long as its temperature is the same, it does not affect the rate of heat transfer. Okay, that's a very good question. So in the world of convective heat transfer, over the years, different people, through either measurements or theoretical analysis, have proposed a bunch of these different correlations that are available to you for use. So if you have a plate of a certain size and if you have air blowing over it, you can look up these correlations to be able to determine the value of H. And once you know the value of H, you can very easily, through this equation, determine how much heat transfer occurs between the two. So in the world of convective heat transfer, step number 1 is to find out the value of H for your specific geometry. So for example, if your solid body is a cylinder and if you have air blowing over it, so that the air will blow over the cylinder in a manner like this, then there are very well known equations that tell you the value of the convective heat transfer coefficient in terms of the diameter of this cylinder, in terms of the velocity of the air, in terms of the properties of the air, and so on and so forth. In this world, in fact, we commonly use non-dimensional numbers. And those of you who have taken a class in heat transfer or fluid mechanics will know that one of the most common non-dimensional number here is the Reynolds number, which is given by ud over nu. U is the velocity, d is the diameter of the cylinder, and nu is the viscosity of the air that blows over it. And the convective heat transfer coefficient is typically represented by the Nusselt number, which is given by hd over k. And typically these correlations are written in terms of Nusselt number is a function of the Reynolds number and also the Prandtl number. Okay, this is the Reynolds number. Please don't make spelling mistakes in the names of people. Okay, it is the nu is given by mu over alpha, mu over rho. I forget which one is called kinematic, which one is called dynamic. I think this is the dynamic viscosity. Kinematic, okay, thank you. So this is the kinematic and that is the dynamic. Okay. I was saying, please don't make mistakes in the spellings of people. Right? My name is Ankur Jain and I want it to be Jain. That is how my parents gave me my name. Right? If somebody makes a mistake in my name, I will not feel good about it, even when I am dead. Right? So all these people are long gone. But I feel that if you make a spelling mistake in their names, wherever they are in their graves, they will curse you from there. Okay? So please don't do that. Especially with Reynolds. His name was Reynolds with a S. There is no apostrophe here. Do you see what I am saying? This is not the number of Reynolds. This is simply Reynolds number, right? So please never use this apostrophe with Reynolds. Okay? Promise? All right. So for example, this non-dimensional correlation, for example, often we write Nusselt number equals C times Reynolds number to the power n times the Prandtl number to the power m, where you can go to well-known textbooks and find out the values of C, n and m. For example, for flow over a cylinder, I think n is of the order of half and m is of the order of 1/3, etc. It all depends on the geometry. Instead of the cylinder, if you have a sphere or if you have a rectangular cross-section body, then this equation might change. You know what I'm saying? But at any rate, you don't have to do the hard work for deriving these equations. These equations are already available to us in a good resource. For example, the most common resource for heat transfer, introductory heat transfer, is this book by Incropera. And do it. When Dr. Tyagi and I were students 25 plus years ago, we had used Incropera and Devitt for learning heat transfer. 25 years later, when we are now teaching the next generation, we still use Incropera and Devitt, right? So this is a very standard, sort of like the Bible of this field. Now there are other authors as well, but if you just search for this, you will find out what I'm talking about. It's an excellent book. Okay. So I just want to connect what we are talking about with lithium-ion batteries. If I have a cylindrical lithium-ion battery, which is indeed the case for most electric cars and electric scooters, the battery pack, it has a bunch of these cylindrical lithium-ion batteries. Not just one, but hundreds, sometimes thousands of these single cells that are arranged sort of in a fashion like this. I'm drawing the cross section here. These cylindrical cells will generate heat, and if we don't remove the heat out of these cells, they will overheat and cause all kinds of problems that we will look at in subsequent lectures. How do I cool these down? The simplest way is to blow air over these bank of cylinders. And if you are working for a startup company that is trying to create an electric scooter or something like that, this will be the key question to you. If I have a fan blowing air over this bank of cylindrical lithium-ion cells, how much heat will you be able to remove? How hot will these cells get? And whether the battery pack will be safe or not. In order to solve that problem, we start really from this very fundamental equation, Q equals H delta T. We find the value of H from correlations like this, right? And that tells us how much heat I can remove from a cylindrical lithium-ion battery. Okay. Surface area also plays a role, and the surface area appears here in Q double prime. Q double prime is watt per meter square. So if the surface area is larger, I will be able to remove more heat. So, just to connect this with cells, if I am designing the cells themselves, if I work for a company like Panasonic that is going to build these cells, and somebody comes to you and says, I have a given volume of the cell, I can either create a long and thin cell, or I can create a short and large cell. The volume is the same in both of them, but the surface area is different. Correct? And the amount of surface area available for heat transfer makes a very big difference, as you can see in this equation. This equation says that the larger the surface area, the greater will be the heat transfer that will occur, right? And therefore, as a battery manufacturer, from a heat transfer point of view, you want to maximize the surface area available for heat transfer. If you blow, the direction in which you blow air also makes a difference. If you blow air like this versus into the plane of the paper, the amount of surface area available is different, right? Or versus at a certain angle or whatever. So you can see that these very fundamental principles of heat transfer can be used to create a first level thermal design of the battery pack. Typically, we spend an entire semester teaching heat transfer principles, right? I am going over it from a very broad overview, condensing the contents of one semester into just one lecture. But you can certainly look at other resources such as Incropera and Devitt for more details of heat transfer. In our short course, we will certainly use a lot of principles of heat transfer, both conduction and convective heat transfer. Another example that I will give to connect this discussion with batteries is the following. The battery pack that I drew here is basically an open battery pack, meaning that I have a bunch of cells and there is air between the cells, and therefore I can blow air over the battery pack. Oftentimes what happens is that I have a solid block in which I will insert multiple lithium ion cells. I don't know if this is clear. Sorry, let me just draw this again. I don't think I did a good job here. What I'm trying to say is that we have a solid metal block in this solid metal block. I will drill holes and make space to insert lithium ion cells. In that case, if I blow air over this body, then the air will not directly touch the cells. The heat generated inside the cells has to first conduct through the solid body to the outside surface of the solid body, and then the air blowing over the outside surface will remove heat. So it's a two-step process. In step number one, heat has to flow from the cylinder through the material of the solid block, and it has to reach the outside surface, and then the air blowing over the outside surface will remove heat. So step number one is conduction. Remember, conduction was the flow of heat through a solid body, right? And then the second step is convection, which is due to relative motion between the solid body and the flow of air. So we need to understand both conduction and convection in order to understand the nature of heat transfer that will occur in this battery pack. Okay, let me actually show you, if I can find here. Oh, sorry. It wants to sell it to me is the problem. Uh, for example, this. So what is happening here is that I have multiple individual cells that are connected to each other and put together as a pack. If I blow air over this, there is only air between these cells. And so the nature of heat transfer will be mostly convective heat transfer. But if these cells were placed inside a metal block with holes in the block, then both conduction and convection will become important. Okay? The third mode of heat transfer is radiative heat transfer. It is probably the most neglected of the three for two reasons. One is it is not as common a factor in most engineering problems, and secondly it is mathematically more difficult to understand and analyze compared to radiation, compared to conduction and convective heat transfer. For those reasons, radiative heat transfer is probably the least studied of the three. It's a little sad in some sense, but that is what it is. For a lot of applications of lithium-ion batteries, radiative heat transfer is not the dominant process. Conduction and convection are much more vigorous and strong compared to radiative heat transfer, and for that reason we will not discuss this too much in our class. For the purposes of thermal management or heat transfer in a battery, conduction and convection are the most important processes. Just to repeat, conduction is the flow of heat within a solid body because of a temperature difference, governed by a very simple Fourier's law in which the thermal conductivity appears, and convective heat transfer is the flow of heat because of relative motion between a fluid and a solid body, which is also governed by a very simple law, except that the convective heat transfer coefficient H, it's not a property of anything, right? Earlier we said that thermal conductivity is 400 for copper, 0.121 watt per meter Kelvin for plastics. That is not as simple for H. For H we need to write these correlations, and these correlations are what will give us the value of H. Typically we use non-dimensional numbers, and the convective heat transfer coefficient is represented by the Nusselt number. The Nusselt number usually a function of the Reynolds number and the Prandtl number, right? So we are done with time, so I'll stop here. All I will say to finish up is that these fundamental concepts of heat transfer we will begin to apply in understanding the nature of heat transfer in lithium-ion batteries as we go forward. So the agenda for the rest of the day is that after lunch we will have a 1.5 hour lecture on the electrochemistry of lithium-ion cells, which will be taught by a local faculty at IIT Ropar, and then I will come in later in the day to teach a tutorial in which we will take these principles of heat transfer and we will put some numbers, and I will solve a few representative problems in order to determine the nature of heat transfer in a very simple battery system. Alright, so are we good to stop at this point? Let's do that. It's past 12:30. What time do you want everyone to be here? Okay, so we will start the next lecture promptly at 2 o'clock. So please go have a good break. I will be around if you have any questions to ask me. And we will see you all back at 2 o'clock. Alright, thank you so much.